Mars, it's not the closest planet to Earth, that's Venus. It's not the easiest place to land, that's the Moon. But for over a century, it's been the stage for humanity's greatest science fiction dreams. And now, our hardest engineering challenge, getting to Mars, isn't like driving across the solar systems. However, it's an exercise in orbital mechanics chess, with Earth and Mars as two moving pieces on a 3D board, and the rules are written by Isaac Newton. At its closest, Mars comes within about 54.6 million kilometers of Earth at its farthest. It's more than 400 million kilometers away. That means the ideal launch window when you can make the trip with the least fuel opens only once every 26 months. Miss it, and you wait over 2 years for another. This is why Mars missions, robotic or human, are planned years ahead. In space travel, time is fuel. And fuel is money. Spacecraft don't fly in straight lines, they follow transfer orbits, curved paths that take advantage of the gravitational dance between planets. The most common for interplanetary trips is the Hohmann transfer, efficient but slow. Using it, a Mars-bound ship would take 6 to 9 months to arrive. The question scientists and engineers now ask is, can we do it faster? Because the less time you spend in transit, the less radiation your crew absorbs, and the less food, water, and oxygen you need to carry. Let's imagine you've been tasked with designing humanity's first high-tech Mars ship. Here's what it needs to survive the trip. Number 1, propulsion. The heart of any spacecraft. Your choice here determines everything: speed, payload capacity. Mission safety options include chemical rockets, powerful, proven, but fuel-hungry, best for escaping Earth's gravity, not for cruising between planets. Nuclear thermal propulsion uses a nuclear reactor to superheat hydrogen, doubling efficiency over chemical rockets. Cut Mars travel to 3 to 4 months. Ion drives, extremely efficient, using electricity to accelerate ions to incredible speeds. Low thrust but can run for months or years, perfect for cargo or slow builds to high velocity. Nuclear electric propulsion combines a reactor with electric thrusters, potentially the best of both worlds. Fusion drives, harnessing the same process as the Sun, not ready yet, but could turn Mars into a week's long trip. Number 2, life support systems. A Mars trip isn't a weekend getaway. You need closed-loop life support, recycling air, water, and even waste. Oxygen from electrolysis of stored water or from CO scrubbers. Water recycling like the ISS, recovering over 90% of onboard water. Hydroponics for fresh food and psychological health. Number 3, radiation protection beyond Earth's magnetic field. Astronauts are exposed to cosmic rays and solar particle events. Shielding options include water walls around crew quarters, polyethylene shielding, storm shelters for intense solar flares. Every spacecraft designer lives under the shadow of Tsiolkovsky's rocket equation. It says, the faster you want to go, the more fuel you need, but the more fuel you carry, the heavier your ship gets, which means you need even more fuel to push that extra weight. It's a vicious cycle, one that makes interplanetary travel hard. Delta V is the total change in velocity a spacecraft can achieve. Essentially, your fuel budget for a Mars mission. You need roughly 9.4 kilometers per second to reach low Earth orbit from the surface, 3.6 kilometers per second to leave Earth and head toward Mars, 2.3 kilometers per second for mid-course corrections and Mars orbit insertion or landing. That's a total of 15 to 16 kilometers per second, plus reserves for emergencies. Why direct launch is a bad idea? If you tried to launch a fully fueled Mars spacecraft straight from Earth, the sheer weight of the fuel would require an absurdly massive rocket, something like the Saturn V on steroids. Instead, the smarter move is to assemble and fuel the Mars ship in orbit and space refueling. The game changer. Imagine this sequence. Launch the spacecraft's core module into LEO. Send up separate tanker missions carrying fuel. Dock and transfer propellant in orbit. Light the main engines only after the ship is ready and fully loaded. Companies like SpaceX are actively developing this with their Starship program. The plan is to refuel in orbit, making interplanetary trips more practical. The Mars orbit rendezvous plan. An even more advanced idea. Pre-position a return vehicle and fuel depot in Mars orbit years before the crewed ship launches. That way, astronauts don't need to carry the return fuel with them. They just top up at Mars and come home. This idea first proposed in the 1960s, dramatically reduces the mass needed to leave Earth. Every day in deep space, astronauts soak up galactic cosmic rays and potential bursts from solar flares. 6 to 9 months of travel on a Hohmann transfer means a significant accumulated dose, not enough to kill instantly, but enough to increase lifetime cancer risk. Shorter trips equals less exposure, but how do we cut that time? The speed versus safety trade-off. More thrust equals faster travel, but also more acceleration forces, more heat, and more energy demands. The spacecraft has to survive the stress, and so does the crew. The sweet spot, cutting the trip from 240 days to 90 to 120 days. Long enough to keep acceleration gentle, short enough to dramatically reduce exposure. Propulsion options for faster trips. Number 1. Nuclear thermal propulsion. A nuclear reactor heats hydrogen to extreme temperatures, which is expelled through a rocket nozzle. Twice the efficiency. Specific impulse of chemical rockets can realistically cut travel to 3 to 4 Hence, NASA's Draco program is already testing this for a potential late 2030s Mars flight. Number 2. Nuclear electric propulsion. A reactor generates electricity, powering high-efficiency ion thrusters. Very low thrust, but constant build speed over time. Great for cargo. Less ideal for crew unless paired with chemical boosters. Number 3. Hybrid systems use NTP for departure burns, then switch to electric propulsion for cruise. Balances speed and efficiency. Number 4. Solar sails and photonic drives. Use sunlight or directed lasers to push ultra-thin sails. No fuel required once deployed, but not yet viable for crewed missions. The sneaky advantage of faster trips. It's not just about radiation, it's about mass. Every extra day in space means more food, water, oxygen, and waste processing. Shorten the trip by half, and you can cut hundreds of kilograms of supplies. And in spaceflight, every kilogram you don't carry is more room for scientific equipment, better shielding, or emergency reserves. Designing a long-duration interplanetary spacecraft is like designing a small, self-sufficient city wrapped in vacuum-rated skin. Everything must earn its place. Mass is expensive. Redundancy is mandatory. And the human factor is as critical as the propulsion system. Let's unpack the must-have subsystems and the design philosophies that govern them. Number 1. Structural frame and materials. Lightweight, strong, and repairable. The outer shell must resist micrometeoroid impacts, thermal cycling, and launch stresses, while being light enough not to bankrupt the Delta. B. Budget aluminum lithium alloys. The workhorse of modern spacecraft. Excellent strength to weight and well understood manufacturing. Titanium and composites. Used where strength and thermal performance are critical. Engine mounts, docking rings, and pressure bulkheads. Multi-layer insulation. The blankets that control heat loss and prevent thermal warping across vast temperature swings. Whipple shields or ballistic layers for micrometeoroid protection. Essential when cruising through interplanetary debris streams. Number 2. Configuration. Modular versus monolithic. To schools of thought, monolithic ship, built on Earth and launched whole. Pros, well tested on the ground. Cons, enormous launcher needed. Single point failure risks. Modular in orbit assembly. Launch modules. Habitat. Propulsion. Cargo. Fuel tanks separately and dock them in LEO. Pros, scalable. In-orbit refueling, easier redundancy. Cons, requires precise docking tech and more rendezvous missions. Most current architectures favor modularity. It lets engineers stage the mission, send cargo and fuel first. The crew launches only when everything is green. Number 3. Internal architecture, living, working, and emergency spaces. A Mars ship is primarily about habitability for months, sleep, work, exercise, medical care, privacy, and psychological health. Engineers divide the internal volume into functional zones. Crew quarters. Private sleeping bunks with soundproofing and personal stowage. Each bunk includes harness points to secure the occupant during thrust or turbulence. Micro-G can make bodies float, which is charming for a day and maddening for a month. Smart lighting systems that mimic circadian rhythms. Warm amber in evening, cool blue in morning. Common areas. A mess module with compact galley and storage, food packaging optimized for minimal crumbs. Poor housekeeping attracts corrosion and microbes. Exercise bay with resistive devices. Tethered bicycles, flywheel systems, or advanced centrifuge modules, essential to prevent bone and muscle loss. Laboratory and engineering day. A well-equipped science lab for sample processing, instrument calibration, and remote sensing analysis. Engineering bay with spare parts, repair tools, 3D printers for on-demand spare fabrication, and modular avionics racks. Medical module. Surgical, capable space with telemedicine links to Earth isolation capabilities for contamination control, both biologically if returning planet samples and in case of crew illness. Waste and recycling, physical separation systems for solids, liquids, and organics. Water reclamation, loop membrane filters, catalytic oxidizers, aiming for more 90% recovery. Solid waste compaction and sterilization. Some waste becomes feedstock for in situ experiments or radiation shielding. Radiation storm shelter, not a metaphor, a heavily shielded safe room, often located at the ship's core and surrounded by water or fuel tanks for extra blocking. NAS. When a solar particle event looms, the crew hunkers down here until the worst passes. Number 4. Thermal control, keeping systems within the sweet spot. Temperatures in space swing harshly, baking in sunlight, freezing in shadow. Electronics, life support, and propellant must stay within specific bands. Active thermal control systems. Pump fluid loops carry heat to radiators, which dump it into space for reactors or nuclear components. The radiators are substantial. Heat pipes and phase change materials store thermal energy during bursts and release it later. Smoothing out spikes, insulation, and louvers provide precise control over radiative cooling. Louvers can open to increase radiative area or close to retain heat. Number 5. Power generation and distribution, keeping the lights on. Power is oxygen to electronics. Choices depend on mission duration and propulsion type. Solar arrays, mature and reliable for inner solar system missions. High efficiency triple junction cells can make sense for short duration transit nuclear reactors, necessary for an EP or continuous high power demands. Offer consistent power, independent of sun angle, critical for missions that may operate in shadow or have heavy electric thrusters. Batteries and capacitors provide surge energy for peak loads during engine burns or communications bursts. Power architecture must be fault tolerant. Redundant buses, cross-strapping, and solid-state protection. Number 6. Avionics, navigation, and autonomy. Long-distance missions demand autonomy. Communication delays may be 4 to 20 minutes one way. Make Earth-in-the-loop control impractical for real-time operations. Navigation, star trackers, inertial measurement units, and optical navigation feed guidance systems. Redundant sensors reduce single-point failure risk. Autonomy. Onboard flight software capable of trajectory corrections, fault detection, and emergency procedures. Machine learning supplements, not replaces, deterministic control logic, communications, high-gain antennas for high-bandwidth science downlink, and low-latency telemedicine. Low-gain omni antennas for emergency broadcasts. Number 7. Docking and EVA systems. Docking is the surgery of spaceflight. Precise, delicate, and mission-critical. Standardized docking rings allow modules and supply ships to connect reliably. Robotic arms for cargo transfer and external repairs minimize risk. EVA letters, EVA suits. Next-gen suits prioritize mobility, dust tolerance, and long-duration life support for surface. AVAS. Number 8. Dust mitigation. The Mars problem you didn't know you needed if you plan to land or return through Martian dust. You must defend sensitive hardware. Martian dust is electrostatically charged, fine, and abrasive. Dust seals on hatches and joints. Electrostatic dust shields that repel particles with oscillating fields. External coatings and sacrificial layers on optics and radiators. Even a small amount of dust where it shouldn't be can degrade performance from solar rays too. Bearings. SL mitigation is non-negotiable. Number 9. Psychological design, habits, REM, and a long tail of boredom. Months in microgravity, cut off from Earth, trapped in a metal tube, is a human problem as much as an engineering one. privacy corners, and personal lighting to give crews control over personal environments. Recreational packs, music, e-books, video libraries. Rotation schedules to balance duty and downtime, with deliberate social events and virtual family calls. Green spaces, even a 1 to 2 cubic meters hydroponic bay with herbs and a tomato plant can dramatically improved morel plants offer tactile, olfactory, and visual relief. NASA's behavioral health research shows that small comforts and predictable routines have reported stress symptoms compared to austere missions. Design is a series of trade-offs. Every design choice cascades into others. More shielding saves crew health but adds mass, which demands more propulsion, which needs greater power, which produces more waste heat, which needs bigger radiators, and the cycle continues. Designing a Mars spacecraft is the art of negotiating these trade-offs until you find a combination that actually fits within launchers, budgets, and human tolerances. If this hits the right level, grounded technical detail, cinematic framing, actionable design insights. If propulsion is the muscle, trajectory design is the brain. Propulsion gets you the capability. Trajectories decide how best to spend it. A good trajectory does two things: minimizes delta V, the fuel cost of changing velocity, minimizes time or optimizes other constraints: radiation exposure, launch cost, phasing. There are only so many geometric tricks in the celestial toolbox. Let's open the box. Mission planners usually use a simplification called the patch-conics approximation instead of solving the full n-body problem for the entire solar system. You break the trip into zones near Earth. The spacecraft is in Earth's gravity well, a two-body problem farther out. The Sun dominates a two-body problem near Mars. Switch to the Mars-centered two-body problem. Each region is modeled with conic sections, and the solutions are patched together where the dominance shifts. This gives excellent first-order plans and is computationally cheap. The Hohmann transfer is the textbook energy minimizer between two coplanar circular orbits are on the same primary. It's two impulsive burns, one to raise the perihelion and one to lower the aphelion for Earth to Mars. First burn, inject into an elliptical transfer orbit that intersects Mars orbit. Coast along that ellipse for roughly half an orbital period of the ellipse. Second burn, adjust velocity to match Mars, so you can be captured into Mars orbit. Why use Hohmann? Because, for low-thrust or impulsive burn planners, it uses the smallest for a given pair of circular orbits at the cost of time. A Hohmann Earth to Mars transfer typically takes 6 to 9 months depending on arrival geometry. There's a trick that looks like cheating: burn your engines when you're moving fastest. The Oberth effect says that a burnout periapsis where kinetic energy is highest converts propellant into the greatest increase in orbital energy. In practical terms, if you want to escape Earth or boost to the Sun, it's more efficient to burn deep in Earth's gravity well than slowly while coasting. This is why gravity assists and deep space maneuvers often use low-energy burns, or small chemical burns at high-speed. Nuclear or electric engines with long duration low thrust can't fully exploit Oberth as effectively as short, high-thrust chemical or NTP burns. So hybrid strategies often combine the two. If you want to go faster without carrying fuel, you can steal momentum from planets. Fly by a planet at high speed using its gravity to bend your path. You exit with a changed velocity relative to the Sun. Historically, gravity assists were mission savers. Number 1, Voyager used multiple planetary flybys to reach the outer planets. Number 2, Cassini used Venus and Earth assists to save V on the way to Saturn for Mars missions. Gravity assists from Venus or Earth are sometimes used to alter inclination, so you can be captured into Mars orbit. Why use Hohmann? Because, for low-thrust or impulsive burn planners, it uses the smallest for a given pair of circular orbits at the cost of time. A Hohmann Earth to Mars transfer typically takes 6 to 9 months depending on arrival geometry. There's a trick that looks like cheating: burn your engines when you're moving fastest. The Oberth effect says that a burnout periapsis where kinetic energy is highest converts propellant into the greatest increase in orbital energy. In practical terms, if you want to escape Earth or boost to the Sun, it's more efficient to burn deep in Earth's gravity well than slowly while coasting. This is why gravity assists and deep space maneuvers often use low-energy burns, or small chemical burns at high speed. Nuclear or electric engines with long duration low thrust can't fully exploit Oberth as effectively as short, high thrust chemical or NTP burns. So hybrid strategies often combine the two if you want to go faster without carrying fuel. You can steal momentum from planets, fly by a planet at high speed using its gravity to bend your path. You exit with a changed velocity relative to the Sun. Historically, gravity assists were mission savers. Number 1. Voyager used multiple planetary flybys to reach the outer planets. Number 2. Cassini used Venus and Earth assists to save V on the way to Saturn for Mars missions. Gravity assists from Venus or Earth are sometimes used to alter inclination or to build up heliocentric energy, but gravity assists exact a time penalty and add mission complexity and risk. Orbital inclination changes are brutally expensive if Earth's orbital plane and Mars' orbital plane are misaligned for your window. You can pay to rotate the orbit. The trick: minimize plane changes by choosing the right launch window, waiting for an alignment where the transfer plane already lines up with Mars. If you must change plane, perform the change at the point where your velocity is lowest to minimize cost. Use gravity assists to shift inclination, much cheaper than propellant alone. There's a whole family of trajectories that deliberately trade for time to achieve ballistic capture instead of burning hard to capture into Mars orbit. You approach slowly and get nibbled gently into capture using Mars gravity plus the Sun's tidal forces. These are attractive because they reduce risky large capture burns and allow mission flexibility, weak stability boundary, and by elliptic transfers exploit delicate gravitational resonances to capture with minimal fuel. They take much longer but save propellant and reduce reliance on perfectly timed big burns. Ballistic capture is particularly useful for robotic missions or sample return architectures where time is cheaper than propellant. If you're trying to slow down at Mars, you don't need to carry all the fuel to brake. Mars' thin atmosphere can do some work. Aerobraking: enter a wide elliptical Mars orbit and skim the upper atmosphere repeatedly. Each pass through the upper atmosphere bleeds orbital energy as drag, lowering apopsis incrementally until you reach the desired orbit. Saves massive amounts of fuel. Requires heat-tolerant structures and precise navigation. Aerothermal loads and dusty atmosphere make it dynamic and slightly risky. Many Mars orbiters have used aerobraking effectively for crewed vehicles. Pure aerobraking is complicated by crew safety and the large thermal protection systems needed. Instead, aerocapture, a single deep pass designed to capture directly into orbit, is attractive if vehicle TPS and guidance are robust. 2 ways to get captured into Mars orbit. Number 1. Powered capture. Fire engines near periapsis to slow down for orbital insertion. Reliable, but rings of Saturn or Delta V expensive. Number 2. Aerocapture. Use a single atmospheric pass to shed enough energy to be captured. Efficient on propellant, but requires excellent aerothermal design, thermal protection system, and near-perfect timing for high-tech human missions. Hybrid plans are common. Use aerobraking to reduce propellant needs for capture, while keeping engines available for contingency-powered burns. You can't just launch any day. The planets must be in the right relative positions. Your transfer ellipse intersects Mars when Mars is physically there. That's phasing. Synodic period between Earth and Mars is 780 days, giving the familiar 26-month windows. Within that window, mission planners pick an ideal launch date that minimizes and aligns arrival for operational needs. Phasing also affects return windows. A crew mission must ensure the crew can return within a viable window. This often dictates surface stay times. To broad classes of crewed Mars missions: short stay, conjunction class, transit 6 to 9 months to Mars, stay approximately 30 to 60 days. Then return with another 6 to 9 month transit. High for quick departure and return because you must leave during a tight window. Long stay, opposition class transit. Stay 12 to 18 months waiting for the planets to realign. Return on a more favorable window. With low rings of Saturn or Delta V requires much more life support on the surface but reduces total mission. Rings of Saturn or Delta V highest low thrust systems don't do instant impulsive rings of Saturn changes. Instead, they spiral slowly, raising or lowering orbit over time. This changes trajectory planning. Continuous thrust arcs replace neat patch conics in planning. For NUP cargo missions, you can do a spiral out MF on LEO and gradually inject onto Mars. Intersecting heliocentric trajectory. Low thrust missions can exploit different optimality. They often need more sophisticated numerical optimization rather than simple Hohmann approximations practically. Low thrust is excellent for cargo, where time is flexible. For crew, where time and radiation matter, you often need higher thrust segments. Without getting tangled in tedious arithmetic, a conceptual rings of Saturn budget for a typical Earth to Mars to Earth again crewed mission includes Earth escape or trans-Mars injection, Mars orbit insertion or capture, Mars surface descent and ascent if using propulsive EDO. Add several km tests, but this is where in situ propellant production changes the math. Return injection and Earth entry rings of Saturn requirements. The key takeaway: where you use atmosphere or in situ resources, you save huge rings of Saturn atmosphere, gravity assists. And ISR your mission designers. Cheapest fuels navigation in deep space blends classical inertial methods with optical fixes. IMUS and star trackers provide continuous attitude and position knowledge. Optical navigation uses photographs of planets, moons, or known asteroids to correct drift and refine trajectory delta differential one-way ranging. Uses simultaneous radio signals to determine spacecraft position with exquisite precision. Autonomy matters, with minutes to hours communication lag. Spacecraft must be able to detect and correct small trajectory deviations by themselves. Good mission plans build in abort options, board to safe Earth return during early phases, board to safe Mars orbit, and allow rescue or delayed arrival, free return trajectories. Let a spacecraft swing by the target and come back to Earth with minimal propulsion if engines fail. For Mars this is harder. But cargo and preliminary mission designs consider partial free return or standby rescue vehicles. Contingency planning is a huge part of mission viability. The best trajectory is one that allows recoverability. Under realistic failure modes, trajectory design is less poetry and more economics. How you trade time, mass, and risk to get the most science and safety for the least fuel. Engineers are the accountants of motion. They make the Sun, Earth, and Mars do what the mission needs through clever timing, well-placed burns, and ruthless optimization. The Mars entry problem. Landing on Mars is famously harder than on Earth or the Moon, and for opposite reasons. The Moon has no atmosphere. You must do all braking with engines. Earth has a thick atmosphere. You can brake with parachutes and heat shields. Mars is in between. An atmosphere too thin for parachutes alone, too thick to ignore, and too unpredictable due to dust storms. This means any entry, descent, and landing EDL system has to combine multiple techniques in sequence, with little margin for error. Step 1. Arrival and entry interface. The spacecraft approaches Mars at 5.5 to 7.5 kilometers per second relative velocity, depending on trajectory and whether you're aiming for direct entry or Mars orbit. First two choices. Number 1. Direct entry. From interplanetary cruise straight into the atmosphere, efficient but brutal, no room for big navigation corrections at the last minute. Number 2. Orbit first, capture into a high Mars orbit. Check systems, then deorbit for a controlled entry, safer, but low costly, for crewed missions. NASA tends to favor the orbit first approach for better safety margins. Step 2. Heat shield and aerodynamic braking. The first atmospheric encounter is hypersonic, Mach 20+. Heat shield design, ablative material, chars and vaporizes, carrying heat away. Peak heating -1500 Celsius, hot enough to vaporize steel. The shield must not only survive but remain stable. Asymmetric heating can cause tumbling. At this stage, careful shaping of the heat shield slows the vehicle by generating a shockwave that keeps most heat away from the main structure. Step 3. Supersonic regime and parachute deployment. Once the spacecraft slows to Mach 2, you can deploy supersonic parachutes, but they have limits. Mars' atmosphere is thin, so even at terminal velocity, parachutes only slow you so much. For small robotic landers, parachutes can handle most of the job. For human-rated systems, parachutes are not enough. You need active propulsion to finish the job. This is why heavy payload EDL systems have shifted towards supersonic retropropulsion. Step 4. Supersonic retropropulsion. This is firing your descent engines while still supersonic. It sounds insane. You're blasting rocket exhaust directly into incoming hypersonic flow, but it's been Then an Earth return test. SpaceX Falcon 9 boosters do this routinely for Mars. You ignite high-thrust engines while still in thin air. Engines fight both gravity and drag simultaneously. Guidance systems must keep you stable despite turbulent flow interactions. Step 5. Terminal descent and landing. And the final kilometer. Reduce descent rate to 2 meters per second for crew safety. Autonomous hazard detection scans the landing ellipse for rocks, craters, and slopes if needed. Perform a short divert burn to find a safe spot. For very heavy landers, the sky crane method can be adapted. Lowering the crew module on tethers to avoid blasting the landing site with engine exhaust and debris. Step 6. Dust, debris, and stability. Mars dust is nasty. It's electrostatically charged. It can infiltrate joints, optics, and radiators. It's abrasive like fine sandpaper. A big crew lander must manage plume surface interaction. Solutions include raised landing pads or legs to reduce dust ingestion, engine gimballing to direct exhaust outward, deployable skirts to contain the dust cloud. Actuation and autonomy during EDL. There is no real-time control from Earth during EDL. Mars is too far for signals to arrive in time. The onboard computer is in full command, making split-second burn and parachute decisions based on sensor input. Key sensors, inertial measurement units, radar altimeters, and Doppler velocity sensors, LiDAR for terrain mapping. Redundancy is critical. One sensor failure cannot be allowed to crash the mission. Entry energy management. Lifting versus ballistic. Ballistic entry. Simple, stable, but limited control over where you land. Lifting entry. Using aerodynamic lift lets you steer during entry. Adjust range, avoid hazards, target specific landing sites. Crewed missions almost certainly need lifting entry to hit precise zones for rendezvous with pre-deployed assets. The 7 minutes of terror. NASA engineers coined the phrase for a reason: from atmospheric entry to touchdown. The vehicle is alone, executing a perfectly timed choreography. A failure in any step. Heat shield, chute, engine. Hazard avoidance means the mission ends in a flash of light on the Martian surface. For human landings, there's an extra challenge. You can't afford to lose the crew. This means building in abort options: either skip the entry and remain in orbit, or abort to a higher altitude and try again. The immediate hostility of Mars. Every survival plan starts with accepting the facts. Atmosphere, 95% carbon dioxide, -1% oxygen, no breathable air. Pressure, 0.6% of Earth's sea level. Step outside without a suit, and your blood boils at body temperature. Temperature. A daily swing from +20°C in sunlight to 100 Celsius at night. Radiation, no global magnetic field. Thin atmosphere, constant exposure to cosmic rays and solar particles. Dust, fine, abrasive, electrostatically clingy, and possibly toxic to humans if inhaled. The surface is not a second Earth. It's an extraterrestrial desert laboratory, and the lab wants to break your gear and your body. Priority 1. Establishing the habitat. On Mars, your first home has to be as engineered as a spacecraft. Habitat designs, pre-deployed inflatable modules, landed months before crew arrival, inflated and checked by autonomous systems. Rigid shell habitats, more resistant to dust and debris impacts, but heavier to transport. Hybrid solutions, rigid central core with inflatable wings for extra living space. Radiation protection. Bury the habitat under 2 to 3 meters of Martian regolith, or stack sandbags and modular sleeves around the walls. Alternatively, use water walls, storage tanks integrated into habitat structure. Doubling as shielding, life support integration, atmosphere revitalization, temperature control. Heaters for the night, radiators for the day. Pressure maintenance, airtight seals and emergency patch kits. Priority 2, power generation and storage. Solar is the default, but dust storms are the enemy. Options, solar rays plus batteries. Lightweight, proven, but vulnerable to dust accumulation. Kilopower nuclear fission reactors. Small reactors producing 10 kilowatts each. Dust-proof, day-night reliable. Hybrid grid. Solar during clear weather. Nuclear baseline for storms and night operations. Dust mitigation. Electrostatic dust repulsion systems for panels. Manual cleaning drones or brushes. Priority 3. Water. ISRU or bust. You can't bring all the water you need, it's too heavy. Mars offers ice deposits under the surface and hydrated minerals in some regions. Extraction methods: heating regolith to release bound water, drilling into subsurface ice layers and melting in situ, using the water not just for drinking, but electrolysis for oxygen, radiation shielding. Crop irrigation, priority for food production and storage. Mars crews will start with packaged food, but long-term missions need in situ agriculture, hydroponics, soil-free plant growth and nutrient solutions. Aeroponics, roots suspended in mist, higher efficiency, less water, LED lighting cycles tuned for growth, and crew morale. Waste recycling into plant nutrients via composting bioreactors, priority 5. Mobility on the surface. Mars is big. Exploration means rovers, crewed pressurized rovers, range hundreds of kilometers between charging, equipped with dust-proof joints, climate control, and emergency shelter capability. Navigation aided by orbital relay satellites and local beacon networks. Small robotic scouts, autonomous terrain mapping, dust storm monitoring, resource scouting, priority 6. Communications back to Earth. Mars to Earth distance means for to 24 minutes one-way light travel time. High-gain antennas for deep space network contact. Mars relay orbiters to provide constant coverage. Delay-tolerant networking software. Messages queued and sent automatically. Priority 7. Contingency and medical systems. Medical support is limited. You can't medevac someone to Earth quickly. Medical module includes surgical capability for trauma, pharmacy stocked for more 2 years, telemedicine with Earth-based specialists, quarantine capability for infections. Priority 8. Coping with dust storms. Martian global dust storms can last weeks and reduce sunlight by 99%. Survival steps. Switch to nuclear or stored power. Seal all habitat intakes against dust infiltration. Halt surface ops unless critical visibility drops to near zero. Use autonomous cleaning systems post-storm to restore solar output. The long game. Building a sustainable foothold. Once survival is secured, expansion begins. More habitats, larger power grids, ISRU fuel production for return flights, greenhouses for psychological and logistical independence from Earth. The Mars ascent challenge. If landing was dangerous, ascent isn't forgiving. On Earth, launches happen from a safe, known pad with years of prep. On Mars, you're launching from an alien surface, potentially in dust storm season, after months of wear on your equipment. The Mars ascent vehicle is the crew's lifeboat. Without it, there's no going home. Propellant. The heaviest problem. You can't bring all your ascent fuel from Earth, that's too much mass. The only viable way to do a long-term crew mission is in situ resource utilization. Sabatier reaction. Extract carbon dioxide from Mars' atmosphere. React with hydrogen brought from Earth. Produce methane as fuel and oxygen as oxidizer. Store cryogenically until launch. NASA studies show that with pre-positioned reactors, you can produce ascent propellant years in advance, ready for the crew's arrival. Mars launch windows. No second chances. The MAV must launch in a carefully timed window to rendezvous with the return trajectory vehicle in Mars orbit. Miss it, and you either burn extra fuel or wait another 26 months for the planets to align to stage versus single stage ascent to stage MAV. Lighter upper stage for orbital insertion. Lower stage stays on Mars. Higher performance, but more complex. Single stage MAV. Simpler, but heavier. Needs more fuel and bigger ISRU production once in Mars orbit. The MAV docks with the Earth return vehicle, a ship pre-deployed and waiting, carrying deep space propulsion for the journey home, light support for the crew, radiation shielding for the long return. This orbital rendezvous is a precision ballet. The two vehicles are moving at 3 kilometers per second relative to Mars, and docking must happen within tight timing windows. You can't just turn around and go home. The return burn must match the launch window for Earth arrival. Avoid excessive re-entry speeds too fast, and your heat shield won't survive. Minimize exposure to solar storms and high radiation regions at Earth. Re-entry from Mars transfer can hit Earth's atmosphere at approximately 11 to 12 kilometers per second, faster than Apollo's lunar return. The heat load is brutal, requiring advanced ablative heat shields, possibly a skip re-entry bouncing. Once off the atmosphere to bleed speed before final descent landing options, ocean splashdown. Simpler, but requires recovery fleet, land landing, more complex, but offers direct crew transport to a medical and debris facility if anything goes wrong with ISRU docking or ascent. The crew may have to wait for a rescue mission measured in years, survive on surface supplies far longer than planned, use alternate emergency return trajectories with minimal science payload. For this reason, mission planners push for dual redundancy to MODs, 2 ERVs, or emergency pre-stage cargo to give the crew a fighting chance when the capsule finally slows under parachutes in Earth's blue sky. It's more than just mission success, it's the end of years of planning, months of danger, and the final step in proving humans can survive and operate beyond our home world. When engineers talk about the best way to fly to Mars, they rarely mean the fastest or cheapest. They mean the way that works reliably, repeatably, and safely every time for Mars. Best is a moving target shaped by technology readiness. What propulsion systems are truly spaceflight proven? Risk tolerance. How much danger will we accept for speed or efficiency? Mission goals. Is this a one-off exploration, or the first step in a permanent presence? Resources, not just fuel and hardware, but political and financial capital. The methods we develop to reach Mars don't stay on Mars. High-efficiency propulsion changes how we explore the outer planets. ISRU technologies make deep space refueling depots viable. Closed-loop life support makes lunar bases more sustainable. Radiation shielding techniques will protect astronauts on decades-long missions. Every innovation tested on Mars becomes a stepping stone to the rest of the solar system. Mars forces us to solve everything: interplanetary navigation, long-duration human survival, remote manufacturing and repair, planetary protection, ensuring we don't contaminate Mars or Earth. In solving these, we lay the groundwork for missions to Europa, Titan, and even interstellar probes. The technical part of going to Mars is hard, but the psychological part, convincing humanity it's worth doing, is harder. When the first crew sets foot on Mars, they won't just be explorers. They'll be proof that humans are a spacefaring species. The moment they breathe recycled air in a habitat they built themselves, drink water they pulled from alien soil, and send back a message: we made it. Something will shift permanently in our collective identity. Fast forward 50 years. Nuclear electric ferries run cargo between Earth orbit and Mars orbit every launch window. Passenger ships carry settlers to pre-built habitats. Mars agriculture exports food to orbital stations. The phrase, launch window, is as common as flight schedule.